Sathyabama Institute of Science and Technology.
Myself, I am Merlin Jenitha, Assistant Professor, Department of Information Technology, School of Computing, Sathyabama Institute of Science and Technology. So in this lecture, I am going to explain AVL tree. So abbreviation for AVL tree is Adelson-velsky Landis AVL tree. So this AVL tree were invented by Adelson-velsky Landis in 1962. Then we have to see the definition for AVL tree. So this AVL tree is the self-balancing binary search tree. So before that we want to know what do you mean by binary search tree. So in binary search tree, each node have maximum 2 children and left child is less than the root node and right child is greater than the root node. So, see this AVL tree is the self-balancing binary search tree. So, first we want to know how to find that self-balancing binary search tree. Using balance factor, we have to find this tree is balanced or not. So here we have to use one formula for finding the balance factor, that is the height of the left subtree minus height of the left subtree. And also this value should be plus 1, 0 or minus 1. Suppose if the value greater than plus 1 or less than minus 1, that tree will be unbalanced. Then we have to make that trees the balance using two types of rotation, that is the single rotation and double rotation. Then we have to find the balance factor value. First we have to find the balance factor value for all the leaf node. So here the balance factor value for the leaf node is, so here left child value is 0 and the right child value is 0. So balance factor value is 0 for both the leaf nodes. So here 11 is 0, then 10 is 0 and 2 also 0. Then we have to find the balance factor value for this 14. So here height of the left subtree is 1 and height of the right subtree is 0. So 1 minus 0, that value is 1. Then here the balance factor value for this 12. Okay. So here height of the left subtree is 1, then height of the right subtree is 2. So 1 minus 2, that value is minus 1. Then here height of the balance factor value for this 5, then height of the left subtree is 1, then height of the right subtree is 0. So the balance factor value is 1. Then we want to find the balance factor value for 7. So height of the left subtree is 2, then height of the right subtree is 3. So 2 minus 3, that value is minus 1. So here all the values in between 0, 1 and minus 1. So this tree is the balanced tree. So this is the self-balancing AVL tree. Then we have to see, so what are the reasons that tree have unbalanced? Based on the 4 cases that tree have unbalanced. So here first case, the insertion into the left subtree of the left child, and second one is the insertion into the right subtree of the left child, then insertion into the left subtree of the right child, then insertion into the right subtree of the right child. So based on these 4 cases, sometimes the tree have unbalanced. Then we have to make the trees balanced using 2 types of rotation, that is the single rotation and the double rotation. Then we have to see when will you have to perform the single rotation. So the single rotation is performed in case 1 and case 4. So here in case 1 is the insertion into the left subtree of the left child. So here we have to perform right rotation from the root node. Okay. So this is the general representation. Now we are going to insert the node x from left subtree of the left child. So here we have to perform the right rotation from the root node. So here K1 is the root node, then this right child of this K1 is moved to the left child of K2. Okay, then how to see the algorithm for the single rotation. So this is the algorithm for single rotation. So initially K1 is the left child of this K2, then left child of K2 is moved to the right child of K1. Then right child of this K1 is the K2. So this is the formula for finding the height. Then we have to return K1. Now K1 is the root node. Then we will see one of the simple example for single rotation. So now, so in this AVL tree, we are going to insert the element 1. So here now we have to check with the root node. Root node is 8. We want to insert the value 1. This value is less than the root node. So we have to insert the value in the left child of left subtree. Then we have to find the balance factor for each nodes. So now the balance factor value is, the root node balance factor value is 2. Now this is unbalanced. Then we have to make that node is balanced using single rotation. So from the root node. So you have to rotate the 8, node 8. So now 5 is the root node. Then right child of this 5 is moved to the left child of that 8. Now then again you have to find the balance factor. Now the balance factor value is 0. Now this tree is the self-balancing AVL tree. Then we will see the next case for the single rotation, that is the insertion into the right subtree of the right child of node. So here right to right we want to insert. So here you have to perform the left rotation. So this is the general representation. So here for example now you are going to insert the node Z in right subtree of the right child. So here we have to perform the left rotation from the root node. So here now K2 is the root node, then left child of this K2 is moved to the right child of this K1. Then this is the algorithm for right rotation, single rotation. Now, so here K2 is the right child of K1, then right child of K1 is moved to the left child of K2, then left child of K2 is K1. So this is a formula for finding height. Then you have to return K2. Now K2 is the root node. Then you have to see the double rotation. So in double rotation is performed in case 2 and case 3. So here in case 2 is insertion into the right subtree of the left child of node. So here we have to perform two single rotation, that is the left rotation and the right rotation. First you have to perform left rotation, then you have to perform right rotation. So this is the general representation for case 2. So here you have to insert the value from right subtree of the left child. So here first you have to perform the left rotation for this K1. Now K2 is moved here, then the left child of this K2 is moved to the right child of K1. This is the first single rotation. Then you have to perform the single right rotation from the root node. Now the K2 is the root node, then right child of this K2 is moved to the left child of this K3. Then you have to see the algorithm for this double rotation. So here you have to perform the two single rotation. First single rotation is the single rotate with left. Then next rotation is the single rotation with right. That value only to be written. This only your root node. Then how to see double rotation using case 3. So case 3 is insertion into the left subtree of the right child of node. So here you have to perform the two single rotation. First you have to perform right rotation, then you have to perform left rotation. This is a general representation for this case 3. So here you have to insert the node from left subtree of the right child. So first you have to perform right rotation from K3. So here K2 of this right child is moved to the left child of this K3. Then you have to perform left rotation from the root node. Now K2 is the root node, then left child of this K2 is moved to the right child of this K1. Then next, this is the algorithm for case 3 double rotation. So here also you have to perform two single rotation. First you have to perform single rotation with right, then you have to perform single rotation with left. Now K1 is the root node. Thank you.